What is the cornerstone of civilization? Math or language? A linguist and an astrophysicist throw down with a look at the movie Arrival. Up next on Science Goes to the Movies. Welcome to Science Goes to the Movies, a look at the stories of science and how they change our culture. I'm Ph.D. Today we are happy to welcome back Emily Rice, professor and astronomer at the College of Staten Island and the American Museum of Natural History. She's going to hold up the astrophysics end of the conversation with Bill Haddican, professor of linguistics at Queens College and the CUNY Graduate Center, telling us about linguistics. Now, all of this is related to the movie Arrival. Welcome.
Hi.
I'm so happy to have you both here at the same time. Thank you. In the 2016 movie Arrival, linguistic professor Louise Banks and theoretical physicist Ian Donnelly must break the code of an alien language in order to save the world.
Every 18 hours, a door opens up. That's where we go in. It's done.
Yeah, that just happened.
What happens now?
They arrive.
They need to see me.
Dr. Banks? Are you insane?
Now that's a proper introduction.
So the first time that Louise and Ian meet, they immediately disagree about the cornerstone of civilization. And Louise, of course, thinks it's language, and Ian thinks it's math and science. Who's right?
You want to go first?
I think they're both kind of right, honestly. Like, I think we should have a showdown right here, obviously. But I couldn't imagine the world without one or the other. I really do think we need both.
Yeah. I mean, if we take civilization to mean something about advancement in terms of social organization and technology, then I think he's right. Ian Donnelly is right? I mean, because all human populations have language, but not all human populations have developed technology and science and that sort of thing the same way. So I think he's more right.
Awesome, I'll take it.
Yeah,
I didn't think it would be that easy,
Wow,
honestly.
I know,
Yes,
I was-
it's definitely the physicist.
We were billing this as a big throwdown, you guys, and you're so respectful. Emily, is math like language?
I think so. I like to think of math as language. Sometimes I feel like I think more in like math or physics than I think in kind of English sometimes.
Really?
Yeah, I'm not sure whether it's just me being a nerd or like I kind of like a lot of metaphors and things like that. And so sometimes I'll say something to people, I'll be like, okay, we're deciding where to go to dinner or something like that. And I'll say, let's collapse this wave function. Which does, that it's...
That is adorably
It's kind
nerdy.
of like, it's talking about quantum mechanics, basically, like the superposition of systems, and you don't know what the system is like until you measure it, and I say, well, I want to measure it, I want to get out of here, I want to get dinner. And it kind of, you can tell who you're with whether or not they get that joke a little bit.
What is the role of time in physics?
So it used to be simple. In classical physics, kind of before this Einstein revolution or the revolution of relativity, time was just like it was an independent variable. We couldn't control it. We measured things against it. It was kind of always on the x-axis, if you think about it graphically like that. And we measured systems and how they changed in time. And like time just marched on. There wasn't anything about time itself that could change. But then when Einstein started to think about the speed of light, how the speed of light should be invariant, he necessarily had to put space and time together. And then time became a variable that can change just like the 3 dimensions of space, and which is just
Mind-blowing.
It's still mind-blowing 100 years later, and it's still mind-blowing. But really that's opened up, general relativity, special relativity. Now our measurements of time can change. We don't experience time differently ourselves, but when we compare the time that we measure to the time that somebody else can measure, we can see a big difference. If we have differences in gravity, that's general relativity, or if we have differences in motion, that's special relativity. And this is just, there's all these kinds of like thought experiments that you can do with this that are just mind-blowing because it's so different than how we experience life, but all the physics experiments show that these things are real. They're theories that have held up to validation time and time again.
And this is what's also so mind-blowing for the character of Louise in this movie, is to understand that time can change and morph.
Yeah, so her experience of time might not be realistic because we still think that time is linear and time only goes forward and goes backwards. That's how time is still different from the other dimensions of space. Because in space, we can move back and forward, but in time, we can only move forward. And so that makes time a little bit different, not quite equivalent to the spatial dimensions, but still, it's exciting to think about the possibilities of having different times.
Bill, a lot of this movie is the Sapir-Whorf hypothesis just kind of shifted into overdrive. Can you describe what the Sapir-Whorf hypothesis says?
Yeah, so the Sapir-Whorf hypothesis has kind of two flavors, two versions. In its strong form, it says that the grammar of the language that we speak strongly determines how we perceive the world and the kinds of thoughts that we can have. We might think of this as kind of the Orwellian version of the hypothesis. So if you remember 1984, George Orwell, there was this language that dictated the kinds of thoughts that the population could have and this sort of thing. And so the strong version of the Sapir-Whorf hypothesis says that the grammar of the language, not so much the words of a language, but the grammar of a language determines the kinds of thoughts that we can have because of the different ways that we experience the world. Weaker versions of the hypothesis say that no, grammar only kind of nudges you to perceive the world in a certain kind of way. It predisposes you to experience the world in a certain kind of way. So those are the two versions.
What do you think as a linguist?
Well, so throughout most of the 20th century, linguists were very skeptical and they thought it was all nonsense. And when I was in graduate school, that was kind of the way that it was talked about and that sort of thing. But more recently, there have been these experimental results that suggest support for the weaker version of the hypothesis. And I think lots of people think that, think that it's on the right track.
Can you give us an example of how the structure, let's take English, we all speak it, of how the structure of grammar would sort of shape the way we view the world?
Yeah, well, can I actually give you an example of comparing two different languages?
Yes.
So the experimental results compare ways that populations of speakers of two different languages might experience the world in slightly different ways, right? And so one set of results that's been kind of influential in the literature has to do with ways that we talk about space in languages like English and in many of the Western European languages that we know, versus languages that have slightly different ways of talking about space. And the language that's been best studied in this way is a Mayan language called Tzeltal, spoken in the Yucatan Peninsula. And this group of colleagues, led by a person named Levinson, went down there and they studied how people there reckon with spatial objects around them. Yeah? In English, we have two different ways for talking about objects around us. We can talk about objects in a relative frame of reference, so I can say that Emily is next to me, or I can say that you're across from me. Or I can talk about the location of objects in absolute coordinates, so I can say that Emily is to the east of me. I don't know, whatever let's say that you're to the east of me. And that's an absolute way. And then some languages, in particular this Mayan language that I was just mentioning to you, only have absolute frames of reference. So they only talk about objects, the location of objects, in an absolute way. Yeah? And so the question that this group of linguists was thinking about is, well, does that actually shape the way that they think about objects around them on non-linguistic tasks?
The sci-fi of the movie tells us that understanding a new language can give you superpowers,
yeah.
or at least change your brain.
Yeah.
Is that true?
Well, whenever we learn anything, our brain changes just a little bit, right? So, I mean, in that trivial sense, I suppose, yeah, when you learn a new language, your brain does change a little bit. But learning a new language certainly won't give you superpowers. No. So Louise in this movie, she's learning this language, this heptapod language, as a second language. And we might expect that, as you know, when we learn a language as adults, we don't learn it as completely as we do when we learn it as children, right? And so we might therefore expect that any of these Worfian effects might be weaker in the second language than in the first language.
The aliens in this movie have a cyclical view of time. And it's reflected in the literally circular structure of their sentences. In English, our sense of time, English is very linear, right? Are there other human languages that are less rigid when it comes to their senses of time?
So lots of languages, maybe all, use spatial metaphors for talking about time. So we say, I'm looking forward to seeing you, or that was back in the 20th century. So we seem to talk about time as location of events as being kind of oriented on kind of this axis in relation to our bodies, this way or that way. And then other languages do things differently. So Mandarin Chinese talks about, so they also have this, they can talk about events in that way, but they can also talk about events vertically, where prior events are above you and subsequent events are below you. So up is previous and down is subsequent, and that sort of thing.
Huh.
So different languages have different ways of talking about time in this way. And then the question you might ask is, well, do speakers of Mandarin think about time or perform differently in different kinds of tasks that involve, different kinds of non-linguistic tasks that involve thinking about time than do English speakers? And the literature goes back and forth on whether or not that's, the evidence is solid.
In English, we sound out our written language from the first to the last character. Chinese characters are called logograms, is that right? What is a logogram and how does that work?
So logograms are units of writing, characters that refer to not units of sound, but units of meaning. And so Chinese is like that in that sense. So each character you see does refer to meaning, but they can also refer to sounds. And so Mandarin Chinese uses these characters to make new words. So new words imported from English, for example, like coffee, use the sounds associated with the characters corresponding to ka and fi to make a new word, for example.
So you do or do not pronounce a logogram?
So in Chinese you can. So it's possible to read aloud in Mandarin, right? It's possible to take a text and read it aloud, and that suggests that the answer is yes. So yeah, because in Mandarin, all of these characters do have sound values as well.
And with a logogram, I'm thinking of hieroglyphics. Does an individual character have a thought attached to it? Is it a picture of something?
So in a purely logographic language, each character denotes just meaning, and like here, denotes just meaning.
Does that mean that math is every character, every number and symbol is a logogram, right? I mean, you see the equal sign, we know what equal means.
Yeah,
you see 2, we know what 2 is.
Sound,
Is that a logogram language?
Yeah,
I feel like it could be, because you look, math puts the symbols together, and the symbols, you can pronounce the symbols all have names.
Yeah.
They each mean something, and then they tell a story.
Yeah, you can read aloud an equation, but you also look at it, and it's not, tan doesn't mean tan like the color. Tan means tangent, and so it means, this particular value about an angle in space, and you can put the things together in different ways, but there's very strict rules about how you put things together, and so you can have math symbols that are gobbledygook, or you can have math symbols that express ideas very completely and very thoroughly.
Yeah.
Emily, Arrival is based on the 2000 Nebula Award-winning novella The Story of Your Life by Ted Chiang. A lot of that story relies on Pierre de Fermat's principle of least time. And that's kind of all I know about it because I'm a history and literature major. Can you explain Fermat's principle of least time?
This is a principle that he came up with in the 17th century, and it's a little bit counterintuitive. It says that if light is traveling, you might think that light would travel the shortest distance between 2 points. That's kind of what we think of as the natural way to do things, the most natural way to do things. But it doesn't. Light actually takes the shortest the path that takes the shortest time between 2 points. And this actually causes some very common optical phenomenon that we see. For example, refraction of light through at a boundary, so between air and glass or air and water, for example. And so when maybe you stick a pencil in a cup of water and you look at it sideways and you see that the image of the pencil is disjointed like that because the light refracts differently through the air than through the water. And it's basically the principle for geometric optics, so how lenses and mirrors bend and change the path of light. And it's very non-trivial. It's not the way that we think things would happen, but it's been a principle that's stood the test of experiments for hundreds of years, and it actually turns out that this principle still works in the new framework, in general relativity, in curved space-time, where light, light reacts to the curved space-time by still taking the path that takes the least amount of time. And so in a curved space-time, that's not a straight line, but a curved line. And so that causes phenomena that we see like gravitational lensing, which is a cool technique that we can use to actually observe even more distant astronomical objects than we could before.
How do you know this in physics? Are you physically doing experiments and figuring it out, or is it all math?
A little bit of both, actually, and that's what science is, or at least that's what physics is in terms of the science. You have the experiments, you write down the numbers, and then you have the idea behind it, the theory behind it, and ideally that theory is based on other things that we know to be true, and then you just kind of build up from there, and you want them to match. You kind of want them to go back and forth and support one another. And if you have a mismatch where theory says one thing, but observation and experiment says something else, then you've got excitement in science, or job security, we also call it.
I mean, Emily, other than sperm, what does Ian Donnelly contribute to this movie?
In the movie, like, not much, which is actually kind of exciting for me as a physicist, as an astrophysicist, to see somebody like in the movie who's just kind of a bit player, like, is kind of cool, because it's like, okay, they don't have to be the star, they don't have to be the center, they don't have to be the linchpin, they can just be, now they're like one of the gang, which is kind of cool. In the book, he does a little bit more. So in the short story, they go a little bit more into the importance of this least time principle, is that this is the principle that really excites the heptapods. So in the movie, it's all about the time and this weapon, and I don't want to give the rest of it away, but really watch this movie 2 or 3 times. But in the book, they advance so far in the language that they're able to communicate about science. And so they're communicating about science, trying to do arithmetic, trying to do algebra, trying to do trigonometry, and nothing really sticks to the heptapods. They don't really, seem to get excited about anything until they talk about the principle of least time. And then the heptapods get super excited. They, repeat it back. They have logograms for it, and that kind of leads the scientists to understand what Louise understands by learning the language.
Emily, Ian is obsessed with finding out whether the aliens what they know about faster than light travel. Why is faster than light travel so important? What is it? Yeah,
faster than light travel is really what we would need to make this alien communication possible. Because even just communicating at the speed of light can be very, very slow. The closest star system to the Earth, which we now know does have an Earth-like size planet around one of the stars very close by, is 4 light years away. So that means if we did want to communicate, we would send a signal. We can say, hey, how's it going, on a radio signal or something like that. They would get it 4 years from now. And then, imagine imagine there was somebody on this Earth size, it's probably a little bit bigger than Earth, planet, that could receive that signal, understand it, turn around and send something back. That's 8 years later. The graduate student that sent out...
8 years, 8 light years? Is a light year the same as a year, 365 days?
A light year is a distance, but it's the it's the distance that light travels in a year.
Okay.
So it's easy to convert. It's a little bit confusing, but it's also, because of that, the way that it's defined, it's easy to convert between distance and time. And so it's 4 light years there, 4 light years back. It takes 8 light years for one 2-sided bit of a conversation. And that's the closest star system and the closest planet that we know about. And so,
good thing we're not trying to swipe right. I mean, this stuff takes time.
Yeah, so we want to grow our neighborhood. That's the thing, is that, if we only have a limited amount of time on this planet, and so, we can only, even at the speed of light, communicate with a very small region of space.
And if we want to communicate anywhere in space, should that language we choose be English or math?
It's math. Well, we've chosen math for the most part, yeah. We encode things. It's basically, it necessarily has to be math. We can encode English a little bit, but I think we know better than that. We know that math is probably at least a little bit universal. There are some things, maybe like prime numbers, or the property of a carbon atom, for example, that should be fairly, like, literally universal. It's the same throughout the universe. And so those are the things that we have tried to encode, sometimes digitally, so sometimes in radio signals, but also analog. The golden record that was on Voyager, for example, has, I think it's a fantastic statement of humanity, the picture of the man and the woman, as well as, I think there's symbols that represent the planets in the solar system. There's also a map to our solar system based on pulsars. in the galactic neighborhood, because pulsars are these things which we think are, you know, kind of remarkable enough astronomical objects that we think alien civilizations will be able to also understand and map these pulsars. And so it's this fantastic just kind of like ray pattern, but it actually tells us where our solar system is in our kind of galactic neighborhood. And so it's a little bit of like a message in a bottle that luckily Carl Sagan and Andrew Ian worked to put on the Voyager spacecraft, which are, you know, running outside of the solar system as we speak. And so, you know, we do it a little bit of both analog and digital. But it's really, you know, it's not just English, it's pictures and it's math and our understanding of the universe that we try to communicate.
We talked about the way we express our relationship with time in English as being linear. Is time linear?
Yes, well, mostly. Time is definitely directional. We can only go forward in time. We can't go backwards in time. And we think that that's because of entropy. In physics, entropy is this property that's unlike any other kind of quantity that any other quantities can kind of change and be reproduced. Like you can move forward and backwards and you come back to the same spot, for example, or you can change energy. Well, when you change energy into different forms, generally energy is conserved, but it actually decreases slightly a little bit, just a little bit, because entropy has to increase. And entropy, we think, is one of the only properties in the universe. Entropy is kind of disorder in a system, and entropy generally has to increase over time. And so we think that because entropy has to increase in a system, that's why time only goes forward and not backwards. But it doesn't necessarily have to be linear, because like I said, time is relative to the observer. And so different people can measure the progression of time differently, we now know, thanks to Einstein and the scientists that worked with him to formulate relativity.
Do you appreciate when, I mean, this makes me think of Interstellar as well. Do you appreciate when movies that are seemingly about science really they become about everything? Yeah. They become about love and connection and future and past and philosophy?
Interstellar might have taken it a little bit too far. You know, when the answer is love or something like that, that's a little bit far-fetched. But yeah, because
wait a minute, maybe the answer is love.
But I love it when science becomes not like, you know, it's like, this is what I also liked about the Ian character, is that usually science is like, you know, the authority that you go to, or the person that has to, you know, make the decisions, save the day, something like that. But I love it when science is much more of a bigger picture thing, more of like a way to understand the world, or, you know, it's a job. Like, he does nothing in the movie.
If science becomes a way for humans to connect. And how did you feel, Bill, about the linguist being like the protagonist?
Yeah, it's great. I was wondering if you had, when you saw the casting for this movie, you were thinking, oh, can we please have the physicist be a woman and the linguist, you know?
I did have that thought, yeah. And I thought it would have been nice, but at the same time, the linguist really drives it. And so, like, some of the movies, I think Interstellar I really wanted to recast, and I wanted to flip the gender roles in that one. But this one I was actually, by the end I was okay with it, and almost partially because the physicist he does a little bit at the end. He kind of recognizes this pattern that ends up being very important, but other than that, very, very little. But I love that the science, you know, and even like linguistics is also a science. It's like the science of language almost, and the science becomes a way of understanding our humanity and our place in the universe, which it really is.
Do you think of linguistics as a science?
Yeah, I mean, not in the same way that physics is, right? I mean, so the techniques we have are different, this sort of thing. The progress that we've made is different. But yeah.
Actually, I would think that the techniques are actually kind of similar. You do experiments, you know, you need to control the variables. You want to, you know, do experiments on certain populations that have certain experiences and things like that. You know, you talked about the recursive grammar. It sounds like computer programming.
And you're using the tools to unlock knowledge, right?
Yeah, that's right.
Overall, the movie and the aliens subtly advocate for collaboration and sharing of science and open data. Where are we with that kind of international collaboration today?
I think it might depend on the field, especially because, you know, certain things are more commercial. I think if something is more commercial or more energy defense oriented, it tends to be, you know, a little bit more classified. But an amazing thing for astrophysics is that it doesn't necessarily have these very immediate applications to something that could be commercial or for defense. And so almost everything is open source. There might be a little bit of a proprietary period so that the scientists that kind of obtained the data have a little bit more time to do the analysis. but a lot of data is publicly available, even from Hubble pictures to real data from the Kepler Space Telescope. There's even projects that very intentionally involve people called citizen science projects. And so the idea is that people and like human eyes and human brains can analyze data even better than computers can. And so this platform in particular is called the Zooniverse, and it's put together so that you can have thousands, sometimes even millions of people look at particular data sets, and basically like how they classify the data can really get us to some interesting science results that we couldn't get out of computers, even the best computers that we have.
Emily and Bill, thank you so much for being here. That's all we have time for today. Whatever we can't fit into this half hour, we'll share on our Science Goes to the Movies Facebook page. And if you want to watch past episodes, check us out at www.cuny.tv under the Science tab, or download our app to keep up with everything related to Science Goes to the Movies all in one place.